Hi again, guys. 2 lessons ago we dealt with the terrestrial carbon cycle. The last lesson we dealt with the ocean carbon cycle. And this lesson we're going to be dealing with solid Earth carbon cycle. That's the carbon cycle between the lithosphere and the atmosphere. As you can see by the video clip, this carbon cycle involves volcanoes. Compared to human emissions, volcanoes only let out a little bit of carbon dioxide out into the atmosphere. Human emissions, anthropogenic emissions, emit more than 100 times the carbon dioxide which volcanoes emit. But even though volcanoes emit so little carbon dioxide compared to humans, volcanoes do still play a very important role in regulating the climate, especially on very long timescales. I'm talking about hundreds of thousands of years. And hopefully at the end of this video we'll have a chance to discuss that a little bit. I would like to emphasize these volcanoes are part of a carbon cycle. So all that carbon dioxide coming out of the volcanoes does find its way back into the ground again. So let's have a look at the solid Earth carbon cycle in a little more detail. The best place to start is with this reaction here, this chemical reaction, and this is called a Ure reaction. Basically, on one side of the equation we have volcanic rock and carbon dioxide, and on the other side of the equation we have limestone and sandstone. So we can look at very simple formulas here. This is a calcium silicate rock, also known as igneous rock. This here is carbon dioxide gas. This here is calcium carbonate, and this here is silicon oxide. So this is limestone, or another word for that is chalk, and sandstone, well, compressed sand really. This formula here is known as an equilibrium reaction. What it is on the left here, we have how the chemicals like to be when it's hot. For example, the calcium silicate and the carbon dioxide, they prefer to be in this form when they're down in the mantle where it's very, very hot. And on this side of the equation, the calcium carbonate and the silicon oxide, they prefer to be in this form when it's cooler, for example, after the carbon dioxide and the volcanic rock have come out of the volcano. They've reacted through weathering with the rain, and then they are now down in the ocean. What I want you to notice is that when it's hot, the carbon in this equation prefers to be in a gas form, it prefers to mix with the oxygen and become carbon dioxide gas, whereas when it's cooler, the carbon tends to be in a solid form, calcium carbonate. Okay, the best place for us to start, I think, is here. The carbon dioxide gets emitted out of the volcano and goes into the atmosphere. Once it's in the atmosphere, it doesn't stay in the atmosphere. It will be recycled between the biosphere and the oceans, and it will stay recycling like that between the oceans and the biosphere for thousands of years. Eventually it will be rained out, and when the carbon dioxide dissolves in the rain, it will form a very weak acid, and this weak acid is known as carbonic acid. This carbonic acid will react with the volcanic rock. When it reacts with the volcanic rock, it'll turn into calcium carbonate and silicon dioxide. So the carbon now is trapped in the calcium carbonate, which gets dissolved into the rainwater again and gets washed into the oceans. Once it's in the oceans, it'll sink to the bottom of the ocean and generally end up on the seabed. If you want to learn a little bit more about that process, you need to watch the video before this one about the ocean carbon cycle. I did forget to mention actually that this process here, when the carbonic acid reacts with the volcanic rock and turns into calcium carbonate and silicon dioxide, this process is called chemical weathering. Much of the calcium carbonate which goes into the oceans is actually used by ocean organic life to make shells, and eventually this life, it dies off and the shells sink to the bottom of the sea and they form limestone. Now, over a very long time the tectonic plates do move, and in this case the ocean crust is being subducted under the continental crust, and it's pulling the limestone with it, and so the limestone is ending up down in the very, very hot mantle where the limestone gets heated. Now if we go back to look at the equation again, we can see that the carbon has ended up in the hot mantle, and because the carbon has ended up on the left hand side of the equation, the carbon prefers to disassociate itself with the limestone and turn into carbon dioxide. This carbon dioxide then builds up a lot of pressure under the continental crust and pushes up a volcano, actually makes the volcano, and eventually the pressure is so much that the volcano actually blows and the carbon dioxide comes back out into the atmosphere again and completes this carbon cycle.
Can you remember earlier in this video I said that the solid Earth carbon cycle helps to regulate the Earth's temperature on very long timescales? We think this is so because 4 billion years ago the Sun was 25% cooler. Another way to look at that is that over the last 4 billion years the Sun has gradually been getting hotter, and now it is 25% hotter than it was 4 billion years ago. The funny thing is, though, that there's no signal of this in the paleoclimate record, and it's definitely something which should be noticeable. If you were to turn the Sun down by 25% today, the Earth would very quickly just freeze over, killing just about all life on it. Likewise, if we were to turn up the heat by 25%, all the water in the oceans would boil, also killing everything on Earth. So it does seem rather funny that the Sun was cooler by 25% 4 billion years ago. But this is a well-established fact. It's just the way stars like our Sun behave over a period of time. Stars like our Sun do get hotter as they get older. As it is over the last 4 billion years, the Earth's temperature has always stayed around, about the freezing point of water, somewhere around that sort of temperature range. And it's thought that this solid Earth carbon cycle here can explain why the Earth's temperature has been kept relatively stable over the last 4 billion years.
Okay, so let me explain the process. Let's say, for example, the Sun heats up, like it has been doing over the past 4 billion years, and this causes more water to evaporate out of the oceans, And because more water evaporates out of the oceans, it means it rains more. And when it rains more, as we know, the carbon dioxide dissolves in the rainwater. So more rain means that there will be more weathering and carbon dioxide levels will be drawn down. Now, as the carbon dioxide levels are drawn down in the atmosphere, this means that there's less of the greenhouse effect, and this cools planet Earth again. And then the cycle starts all over again. Okay, that's the end of this lesson. I'm just going to leave you with a little clip showing the power of a volcano.
This is a photographic reconstruction of an eruption which blew the side off Mount St. Helens. It happened in 1980 in Northwest America.